Today, ladies and gentlemen, is going to be one of the greatest days of your life because we are going to be exploring that which Sir Isaac Newton and Gottfried Wilhelm Leibniz happened to both discover around the same time during the years of 1665 and 1675. They both developed the same ideas that have been come to be known as calculus. And what we're going to look at today is something called the derivative. It's very exciting stuff, and it's what this limit thing has been leading up to, and it's a culmination of a lot of the things that we've been doing throughout the years. So, what is a derivative? Well, it's a rate of change. And we know that a rate of change is slope. Change of y over change of x. And the way we find slope is we take y2 minus y1, or in function notation, it would be f of x2 minus f of x1, and divide by the change in the x's, x2 minus x1. Let's look at a visual representation of this here. So we have this curve here, and I have 2 points, A and B. And those 2 points determine or define a secant line to this curve. It cuts the curve in 2 places. And we could find the slope of those two by taking f of x plus h minus f of x. Now, what's this that x plus h thing, Mr. Schnack? Well, instead of calling it x1 and x2, here's x. This other x value for A is going to be h units away from it. It might be 1 unit away, it might be 2 units away, it might be really close. We don't know, but it's h units away from x, so we call it f of x plus h. And the slope is going to be the difference of those y coordinates over the difference in the x coordinates, and that becomes f of x plus h minus f of x over h. And look what happens if we move these points close together. The slope changes, yes? And what we're actually finding when we talk about the derivative is the slope of the line that is tangent to the curve, meaning it only touches the curve in exactly one place at that point. So what I can do is, if I make h really small, I'm getting closer and closer to a line that is tangent. But I can't make h exactly 0 because, well, look at the picture. That's what happened. There is no line that I can find the slope between. The change in the x's would be 0 and the change of y's would be 0, and that doesn't help. So what do we do when we want something to become smaller and smaller and smaller and smaller? Well, I'm glad you asked, because what we're going to do is we are going to take the limit as h goes to 0. And this will find us the slope of the tangent line, or you'll see it called the gradient of the tangent to that curve. And this is an instantaneous rate of change. If I move to a different point, notice the tangent is different there. If I move over here, now the tangent is positive. So as we change our point on the curve that we want to look at, the tangent line, the slope of that tangent line, is going to differ from one place to another. This is what we're talking about when we talk about a derivative. And the notation that we use is f prime, f apostrophe, x. That is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now notice we can't do a direct substitution because, well, h is 0, so we have something over 0. That's bad. We'll talk about how we evaluate this limit in just a minute. But another notation that you'll see denoting derivative is dy dx. It means take the derivative of y with respect to the x variable, and that's going to have a lot more meaning as we get deeper into the calculus. Okay, so lot just hit you. your head might be spinning. Let's go ahead and use this. Let's go ahead and use this in a couple examples. All right, so find f prime x. That means find the derivative, the instantaneous rate of change of this function. And then hence find the gradient of the function at x equals -3. So this is a quadratic. And we're looking for the tangent, pretend those are tangent, but the slope of the tangent when x is -3. This tangent is going to differ depending on what value of x we're looking at. So let's go ahead and use this definition of derivative. F prime x equals, I'm going to write it down, f of x plus h minus f of x all over h, but I forgot my limit. It's important that we write that. Limit as h goes to 0. So, this is a function composition on top. Until I take the limit, it needs to be written. So, f of x plus h, so that's going to be 2 times x plus h squared plus x plus h. That's this part. And I'm going to subtract f of x. And this is all over h. And now we get to do some algebraic simplifying. So limit h goes to 0. Don't forget that. Don't leave it off. We have to expand the yellow highlighted part. So 2 times x squared plus 2xh plus h squared plus x plus h minus 2x squared minus x. I distributed this negative in all over h. Limit h goes to infinity. Not infinity. How about 0? Two x squared plus 4xh plus 2h squared plus x plus h minus 2x squared minus x all over h. Let's combine like terms. And what should happen, if you've been doing things right, is you should see that every term that does not have an x is going to become 0 with something else. So what I'm left with is 4xh plus 2h squared plus h all over h. Now all these terms have h's. That's great. I can cancel. I can divide each term by h. That's cool. That's excellent. That whole over h business that was allowing me to not be able to do a direct substitution will now be gone. That's great. 4x plus 2h plus 1. Okay, now let's do our direct substitution. This is equal to, if I plug h equals 0 in, I'm left with 4x plus 1. This is our derivative, ladies and gentlemen. When you are done taking the derivative, there should be no more h's in here. It should just be a new function of x. So now I forget what was the other part of this question. It said find the gradient of the function in x equals -3. So this means we want the derivative evaluated at -3. So 4 times -3 plus 1 is -11. So the slope of this quadratic function at x equals -3 is going to be -11. So that tells us that this quadratic is very, very steep and decreasing at that point. Let's go to the graphing calculator and have a look at this visually. So graphing our function, we see this, and here's x equals -3, and it does look like that graph is pretty darn steep right there. If we were to draw a tangent line along at x equals 3, we'd have a very steep line that's going down, that's decreasing. So we can actually use the calculator to see if we'd found the derivative correctly. So what we can do, go into Menu, Analyze Graph, dy dx, and I want to know when x equals -3. So I type -3, push Enter, and look, the derivative at -3 is -11. The slope of the tangent line to the curve is -11. Wicked fun, wicked awesome. Next video, we're going to look at a couple more examples.